In the previous lecture, we had been looking at vectors, in particular how to represent them algebraically, and then we looked at the product of vectors and defined a scalar product which we wrote as a x b x plus a y b y plus a z b z, and a vector product which gives me a vector a cross b and in a short way I wrote this as determinant of a x, a y, a z, b x, b y and b z, and I had asked you to check that this gives the correct answer. We define these two products in this manner because they satisfy certain transformation properties of vector components under rotation. Let us look at these products now slightly more carefully. So, let us look at the dot product A dot B, which is A x B x plus A y B y plus A z B z. This can also be written as magnitude of A times magnitude of B times cosine of theta, where theta is the angle between A and B, and theta is the smaller of the angle. So, theta is less than 180 degrees. In particular, if I look at the unit vectors along x direction, y direction and z direction, we find that I dot I is same as j dot j, they are all equal to 1, because their magnitude is 1 and the angle between j and j or k and k is 0. Similarly, I dot j is 0, so is j dot k and so is k dot I. Notice that the dot product or the scalar product can be both negative and positive, because cosine theta can be negative or positive. Similarly, if I look at two vectors A and B, then A cross B, which I can write as the determinant I j k A x A y A z B x B y B z is also equal to magnitude of A times magnitude of B times sine of theta, where theta is the smaller of the angle between A and B. So, theta is less than 180 degrees times a unit vector in direction n, where n is perpendicular to both A and B. So, it is perpendicular to the plane formed by A and B. So, it will be somewhere like this, maybe coming out of this plane of the board. How about whether n is this way or this way? This is answered by the right hand rule. You turn A towards B through the smaller of the angle, and the thumb gives you the direction of the vector product. So, in this case n would be going down. You can see that A cross B is going to be equal to minus B cross A, because the magnitude will remain the same. but the direction of n would change, because now you will be turning B towards A. This is also clear from the components if you look at them carefully. So, this is how the cross product works. In particular, if I look at the unit vectors I, j and k in x, y and z direction, then I cross I is 0 and so is j cross j, because the angle between them is 0 and so is k cross k. On the other hand, I cross j is equal to k, j cross k is equal to I, and k cross I is equal to j. These are the relationships between unit vectors. Let us now look at one or two examples where you see these relationships carefully. First, I want to show you that A cross B through an example is really equal to A B sin theta times n, where n, as I told you, is in the sense of rotating A towards B through the smaller of the angles. So, let us for simplicity take this as x axis, this as y axis. Consider B to be a vector, unit vector in x direction. So, B is equal to I, and consider A vector to be in this direction, which is 45 degrees from the y axis or the x axis. So, A is equal to minus I plus j. You can see that the magnitude of A is square root of 2, magnitude of B is 1, and the angle theta between them is 135 degrees. So, therefore, A B sin theta n is going to be equal to sin of 135 is 1 over root 2 is going to be equal to 1 times n. Turn A towards B through the smaller angle, and that gives you a direction the opposite to z axis. So, this is going to be minus k. Let us see if you get the same answer if I explicitly do component wise a vector product. In that case, A cross B would be minus I cross plus j cross I cross I is 0 and j cross I is minus k. So, you see both give you the same answer. Now, I want to demonstrate to you that A cross B gives you a vector that is perpendicular to both A and B. Since A cross B is equal to modulus A modulus B sin theta n, where n is perpendicular to both A and B, that means that A dot A cross B, which is equal to modulus of A cross B cosine of theta, let us call it theta prime, because now this is the angle between A and A cross B, should be 0, because A cross B is in a direction perpendicular to A, and so should be B dot A cross B, which is equal to modulus or magnitude of B, magnitude of A cross B, cosine of, let us say, theta double prime. Again, since A cross B is supposed to be perpendicular to A and B both, this should also be 0. So, let us take an example. Let us take A to be a vector, let us say 2I plus 3j plus k, and B to be a vector, let us say minus 3I plus 4j minus 5k. We want to take their cross product or vector product and show that the resulting vector is really perpendicular to both A and B. So, what we will do is we will calculate A cross B and then take dot product with A and take dot product with B. So, let us do that. So, A cross B is going to be equal to I j k. Let us see what the vectors were 3 2 3 1. So, 2 3 1 and minus 3 4 and minus 5, minus 3 4 and minus 5. So, the cross producted I minus 15 minus 4. So, minus 19 plus j minus 3 plus 10. So, plus 7 plus k 8 plus 9 17. So, this gives me a vector minus 19 I plus 7 j plus 17 k. This is A cross B. Let us take A dot A cross B, which is equal to 2 I plus 3 j plus k dotted with minus 19 I plus 7 j plus 17 k. Now, I can use the distributive property and show that I dot I is 1. So, this is going to be minus 38, I dot j is 0, I dot k is 0. So, no contribution from here, plus 3 would multiply only the j component plus 21 and k would be plus 17, which is equal to 0. Since A and A cross B both magnitudes are non-zero, this can only happen if the angle between A and A cross B is 90 degrees. I leave it for you to show that B dot A cross B is also 0. Thus, we see that A cross B is perpendicular to vectors A and B both. Let us now look at geometric interpretation of a dot product or cross product. Of a vector product. A cross B magnitude is nothing but magnitude of A as magnitude of B times sine of theta, where theta is the angle between them. So, if there is a vector A and there is a vector B, an angle between them is theta, you can see that A cross B is nothing but A times B sin theta. This is B magnitude. So, this is B sin theta. So, this is the base times the height of this parallelogram, and therefore, magnitude of A cross B is the area of a parallelogram formed by A and B. Next, we look at A cross B dotted with C. This I leave for you to show that is AX, AY, AZ, BX, BY, BZ and CX, CY and CZ determinant. Its value is equal to this, and this has a geometric interpretation of if I form a parallelepiped by vectors A, B and C. It is the volume of this parallelepiped. So, that is the geometric interpretation. Since I can write A cross B dot C as this determinant form, this also shows, since determinant does not change if I change its rows twice, this is also equal to A dot B cross C. This is also equal to C dot A cross B, which is same as this, and there is one more term, this is also equal to B dot C cross A. All these are equal. This is cyclically the dot product and cross product go like this. So, this is a general review of vectors that we have done, and now we are ready to look at equilibrium of a body under applied forces. As I said in my previous lecture, by equilibrium, in general we would mean that the acceleration is 0, but here we would also mean that the body is static. It is not moving. So, let us look at the conditions that are necessary and sufficient to make sure of that. Let us go step by step and look at a point. Suppose I have a point mass and I want it to remain stationary, but there are several forces applied on it. So, this could be F1, this could be F2, this could be F3, and this could be F4. If the body does not move and its acceleration is 0, that means the net force on the point mass under equilibrium is 0. And that means, in this particular case, that F1 plus F2 plus F3 plus F4, the vector sum of all these forces gives me the net force, and that must be 0. In general, if there are more than 4 forces, there may be n forces, I should have one condition, summation over I all forces is equal to 0. This is one condition for equilibrium. So, there could be more than one force, more than 4 forces in all sort of directions, this direction. Sum of all that must be 0 in order for the point mass to be in equilibrium. I have been talking about point mass because in that case we are all just up, it cannot do anything else, just move. On the other hand, in engineering problems, we do not always have a point mass. We have extended bodies. For example, I could have a beam that is supported on 2 pillars and there is a load here. And the 3 forces, that is one force applied by the support in this direction, force applied by the other support in this direction, and the load. Not only these 3 forces should be 0, there should be some other conditions. What are those conditions? And we are going to look at them. When we apply force on an extended body, experience tells us that the extended body not only can move, it can have some more effect on the extended body. For example, if I put the support here, one support here, and apply the force this way, you know that this body is going to rotate like this. Other effect that the force can have is, again looking at the same beam being supported by 2 supports, 2 pillars, and if I apply a force here, it could bend like this. So, there are all sorts of things that a force can do besides just giving it a motion. It can make the body rotate or make it bend. In this course, we are going to assume that this does not happen. The body is so rigid, its internal forces are so good that they adjust and do not let the body deform. This is called as rigid body approximation. The body is so rigid that it does not deform at all. So, the only two effects then the force can have is number 1, move it, number 2, rotate it. So, we are going to consider these two things in this course for equilibrium. The tendency to rotate or strength of a force to rotate is measured by a quantity called the torque. By the torque it generates. For example, suppose I have a body which is held at one point, and if I apply a force in this direction at distance at displacement r from the point at which it is held, then the torque is given by r cross f, or the vector product of the displacement times the point at which the force is applied. Experience tells us farther the force from the point at which the body is held, more it rotates, more it tends to rotate. So, therefore, the distance is important. The vector product is important because if the force is applied in the direction of this point, if the force is along the same direction, it will not rotate. So, vector product in that case would be 0. So, this is how the torque is defined. So, let us write now torque tau from the origin O is going to be given as r measured from O cross f. RO measures the point at which the force is being applied compared to the origin or the point at which the body is being held. But naturally, when you define torque like this, it is an origin dependent quantity. For example, let us take x, y and z axis. Let us take a body here. If I apply a force at this point, in this origin, the torque would be r cross f, let us say r o. On the other hand, if I have a different frame of reference centered at O prime, the torque you can see is going to be different. How do we relate the direction of torque to direction of rotation? So, if torque is given by r cross f, it is going to be equal to magnitude of r, magnitude of f, sine of theta n, where n is the vector that is given by this thumb when r is turned towards f through the smaller angle. The tendency of rotation is also the same. If n is the direction of torque, the fingers, right hand fingers, give me the direction of rotation, as you can see. If there is a body here held here, if the force is this way, then r cross f is going to go into the board. So, body you can see has a tendency to rotate this way. On the other hand, if the force is in this direction, then R cross F is coming out of the plane of this board, and the body has a tendency to rotate in this manner. So, this is how we relate the torque direction and the direction of tendency of rotation. So, if we want that in addition to not moving, the body also does not rotate for equilibrium, then the torque on the body should also be 0. So, two conditions for are A, the sum of all the forces F I be 0, then the body would not move, and B, sum of all the torques applied on the body should also be 0. You may ask, I have just now said that torque depends on the origin, and I have not put any origin here. Once you satisfy this condition that sum of all the forces is 0, the torque, the net torque is going to be independent of the origin, as we will show later. So, therefore, this condition is also independent of the origin once I make sure that summation of F I is 0, and these two conditions are necessary and also sufficient for equilibrium of a body. Let us take an example, a simple one to start with. Suppose I have a beam which is being supported on a block of, say, cement. The beam is lightweight, so I can ignore its mass, and suppose it is holding a weight of 1000 newtons. What force F should I apply in order to hold this weight? Let us say this distance is 1.5 meters and the load is being held at a distance of 1 meter. If I look at the beam, the forces that are being applied on the beam are the force by me, force of 1000 Newton at a distance of 1 meter from the support, and the support would also be applying a force N. So, first condition, that summation F I is equal to 0 gives me, if I assume this to be the y direction, that j unit vector F plus n minus 1000 is equal to 0, or F plus n is equal to 1000. That is condition 1. On the other hand, torque should also be 0 about any point I take. So, let us take this point about which I am going to take the torque, and then you see that 1000 Newton gives me a torque clockwise, the F gives me a torque counterclockwise, and they should both balance each other. So, if I write summation tau is equal to 0, since all the torques are in the same direction, up or down, I can straight away write this as F times 1.5 minus 1000 times 1 should be equal to 0, or the force is 1000 over 1.5, which is 2000 over 3, or 667 newtons approximately. So, you see, this is how I am going to apply the condition for equilibrium for the force and the torques. For the second example, let us take the case of lever that we use every day. Let us suppose we have a very hard rod which is put on a brick on the ground. Let us say the height of the brick is 6 centimeters. Let this length be 0.1 meter, let this length be 0.9 meters, and I am trying to lift a load which is pushing the rod down of 1000 newtons by applying a vertical force here. What all would happen? Suppose initially I ignore the friction between the brick and the rod, then you can see that on the rod the forces that we are applying are number 1, the force downwards, number 2, the force downwards because of this load 1000 newtons, and at this point the brick is going to apply a force perpendicular to the rod in this direction. You can see right away, if there is no friction, this N is going to have a horizontal component that is not balanced. So, the rod is going to have a tendency to move this way. In order that the rod does not move, there should also be a frictional force between the rod and the brick. So, we are going to assume that there is a sufficient frictional force that prevents the slipping to the left. So, let there be a frictional force in this direction F, let there be a normal reaction N, let there be the force that we are applying F vertically down, and let there be a force 1000 newtons here. This distance is 0.1 meter, this distance is 0.9 meters, and the friction is sufficient to prevent slipping. We want to know the value of F. How much force should I apply down in order to lift this weight of 1000 newtons? Again, we are going to apply the two conditions that we talked about. This is the brick of height 0.06 meters, 6 centimeters. Let this angle be theta, this is 0.1, this is 0.9, this is N, this way is frictional force F, this is F, and this is 1000 newtons. So, when I first write the force condition, summation F I is equal to 0. Let us write its x and y components. So, summation F I x is equal to 0 gives me N sin theta, which is in the negative direction, plus F cosine of theta is equal to 0. Similarly, when I write summation F I y, the force component y direction is 0. This comes basically by writing force in terms of I and j and making each component of the vector 0. This gives me N cosine of theta plus F sine of theta minus 1000 minus F is equal to 0. So, these are the two conditions for the force balance. How about the torque? For the torque, let us choose a convenient point, because it does not matter which point I choose. Let us choose the support right here as the point about which I will take the torque. Then you can see that this F has a tendency to rotate the rod clockwise, and this has a tendency to rotate counterclockwise, and therefore, two are working in opposite directions. The torque is all going to be, if we take this plane to be xy plane, torque is going to be in k or minus k direction, and therefore, I can just write the scalar numbers right away. Is going to be equal to, clockwise would give me a minus k. So, F times 0.9 cosine of theta with a minus sign plus 1000 times 0.1 cosine of theta is equal to 0, and therefore, F comes out to be 1000 over 9, which is roughly 111.11 newtons, and that is your answer. If you wish to find what N and F are, those can be found from these equations. you will require sin theta and cosine theta for that, and that you can obtain from this triangle. So, in these two examples you saw that I have used terms like normal reaction, frictional force, moments, torques, etc. So, now we will specialize and look at each of these things more carefully. For example, if I take a support, in which direction does it apply the normal reaction? In which direction are the frictional forces? What are different types of frictional forces? We will study movements in slightly more detail to understand how it can affect the motion and what special movements are. So, we will take these topics one by one. I want to start by discussing moment of a force, moment or torque of a force. As indicated earlier, the moment of a force or torque is given by R cross F, where R is a vector from the origin to any point on the line of action of the force. If there are many forces, then the total torque is going to be equal to sum of all these torques, which is going to be summation R I O cross F I. Let us see that through an example. So, if I am calculating the moment tau, which is R, I am dropping O now, it is understood that it is depending on the origin, cross F is going to be equal to its component x direction is going to be equal to y f z minus z f y plus component in the y direction is going to be z f x minus x f z plus the component in the z direction is going to be x f y minus y f x. So, let us take a simple two dimensional example. Let there be a force of 20 newtons acting along the line which is passing through say 1, 2 and 3, 3. So, that if I were to write the force as a vector, it would be 20 times a unit vector in this direction, which I can write as 20 times a vector in this direction would be 2 I plus j divided by square root of or the magnitude of this vector 2 I plus j, which will be square root of 5. So, this is the force that is being applied. So, the force that we are applying is F equals 20 2 I plus j over square root of 5. It is being applied along the line which is passing through 1, 2 and 3, 3. Let us calculate the torque about the origin by first taking R from 0 to 1, 2. So, that this vector is going to be I plus 2 j, and we are crossing it with F, which is going to be nothing but I j k, the determinant way. I is 1, 2, 0. For the force, it is 40 over root 5. J component is 20 over root 5 and 0. This gives I component 0, j component 0 and k component is going to be 80 over root 5 minus 20 over root 5, which is 60 over root 5 k. That is the torque. What will torque be if I take r instead to be the vector from 0, the origin, to 3, 3? Let us calculate that. So, that vector is going to be 3 I plus 3 j. Force of course is 20 over root 5 2 I plus j newtons. So, if I calculate torque, which is r cross F, it is going to be equal to I j k, this determinant, 3 3 0, 40 over root 5, 20 over root 5 and 0. Again it gives only non-zero component in direction. K is going to be equal to 60 over root 5 minus 120 over root 5, which is minus 60 over root 5 k. The direction seems to be opposite. I must have made a mistake in the previous part. Let us check that, and yes, indeed there is a mistake. This should be minus, this should be plus. So, in the previous part also the answer was minus 60 over root 5 k, and this part also the answer we get is minus 60 over root 5 k. And therefore, you see that no matter where I take the vector r to be along the line of application of the force, the torque comes out to be the same. This is also an example of transmissibility. Of force vector that we talked about in the previous lecture. As I said earlier, if there are many forces on a body, origin x, y, z, there are many forces working, F1, F2, F3, F4 and so on, then the total torque would be equal to summation of individual torques, which will be equal to R1 cross F1 plus R2 cross F2 plus R3 cross F3 and so on, which is equal to summation Ri cross Fi, where Ri is the vector from the origin to any point on the line of action of the force Fi. If the forces are concurrent, that means they all meet at some point, this may be one force, this may be the other force, this may be the third force, fourth force, fifth force and so on. Then the torque, I can take this point where they meet to be the point where I am going to take the torque displacement, and therefore, this is going to be Rj. Let us call this Rj cross Fi, which is equal to Rj can be taken out because it is the same for all forces, cross Fi, which is nothing but Rj cross F total. So, if all the forces meet at a certain point, the torque due to all the forces is equal to the torque of the total force cross with the direction up to that point. This is known as Vagnon's theorem, and true only when all the forces are meeting at a certain point. In general, since the torque is origin dependent, therefore, if I take two particular frames O and O prime, x, y, z, x prime, y prime, z prime, tau O is not going to be equal to tau O prime for a given set of forces F1, F2, F3, F4 may not even cross them, F5 and so on. However, there is a very special circumstance under which the two torques are equal, and that is when summation of Fi is equal to 0, and I am going to show that to you. Let us take two different frames O, O prime, x, y, z, x prime, y prime, z prime. Let the distance vector from displacement vector from O to O prime be r. I am going to draw in green the forces. Let this be F1, let this be F2, let this be F3, let this be F4 and so on. Then the torque about O prime is going to be equal to R I prime cross F I summed over I, and torque about O is going to be summation R I cross F I, where R I and R I prime I take to be the vectors. Let me draw them in blue, touching at the same point. So, let us say if I extend this force like this, this could be R 1, this could be R 2, and up to this point this is R 1. Or for F 4, this is R 4 and this is R 4 prime. Oh, this is sorry, this should be R 1 prime. So, if I now take the difference between tau O prime minus tau O, this is going to be equal to summation R I prime minus R I cross F I. And from the figure it is clear that this is R 4 prime, this is R and this is R. So, R I prime plus R is equal to R I, like R 4, this is R 4 is equal to R plus R 4 prime. Similarly, R 1 is equal to R plus R 1 prime. So, R I prime in plus R is in general R I, and therefore, R I prime minus R I is equal to R with a negative sign, and therefore, tau O prime minus tau O is equal to summation I minus R cross F I. R being the same vector, I can write this as minus R cross summation I F I. That is the difference between the torques taken about point O prime and point O. So, let us write this again, tau O prime minus tau O is equal to minus R crossed summation I F I. R is a vector from O to O prime. Thus, if the total force summation F I is equal to 0, this implies tau O prime is going to be equal to tau O. The torque becomes independent of the origin because I took O and O prime arbitrarily. This is what I promised you earlier. I will show that if the total force on a system is 0, then the torque is independent of the origin. No matter about which point I take the torque, it will always come out to be the same. A very special case of this is something called a couple, which is used in engineering mechanics quite a lot. And what is a couple? A couple is, suppose I take a body, apply a force in one direction, apply a force in the opposite direction minus F, and they are displaced parallelly from each other by a distance d, then net force F minus F is equal to 0, and the torque need not be 0, because the forces are displaced from each other is going to be magnitude of F times d, where d is the perpendicular distance between the two, and this is known as a couple or couple moment. It is indicated either by this symbol, where these two arrows show the forces applied, or a symbol like this. So, it is a pure moment without any force. Thus, a couple is a force or two forces F minus F displaced by parallel distance between them d, and its moment is given by F d. Since the net force is 0, a couple, the same couple can be generated by different kinds of forces. For example, I could have a force F 1 going the other way, minus F 1 displaced by distance d 1 from each other. This would be equivalent to a force F 2, which let us say is minus F 1 divided by 2, but the distance d 2, which is twice d 1, which will also be equivalent to a force F 3 minus F 3, let us say, which is equal to 3 times F 1, but displaced from each other by a distance of d 1 over 3. They all three of them represent the same couple, because the net force is 0. So, there is no effect of the force. So, let me just recap what all did we do in this lecture. 1, we looked at vector products in detail. Then we looked at equilibrium conditions and found that summation F I is equal to 0 and summation torque I is equal to 0 are both necessary and sufficient condition to ensure equilibrium. Then we started looking at different aspects of equilibrium separately, and third, we looked at moment of a force and found that tau the total torque tau I summed over is equal to R I cross F I is origin dependent, but becomes independent of origin if total force is 0. Let me rewrite this again. Tau is independent of origin if summation F I is equal to 0, and then we looked at a very particular special kind of torque under these circumstances called a couple, which is two forces, equal and opposite forces separated by a parallel distance d. In this case, the force magnitude times d is the couple moment, and the direction you can find by right hand rule or the cross product rule yourself. In the next lecture, we will look at how to define the moment about an axis or a couple about an axis, and then go on to discuss other things about equilibrium.